Tonight we're going to travel to the edge of everything, not the edge of our solar system, not the edge of our galaxy, the edge of the observable universe itself, a boundary so distant, so ancient and so strange that the moment you truly understand what it means, something shifts inside you, a quiet vertigo, a kind of beautiful, terrifying awe that you cannot unfeel. Because the distance to the edge of the universe is not simply large, it is wrong. It is broken in the most fascinating way imaginable. And tonight, together, you and I are going to sit with that wrongness until it becomes something that feels almost like peace. Here is what most people never get told. When scientists say the edge of the observable universe is approximately 46 billion light-years away, they are giving you a number that sounds like an answer. But buried beneath that number is a truth that rarely gets mentioned in classrooms or documentaries. A truth that changes everything. Light that has been travelling since before the Earth existed, since before the sun was born, since the very first stars ignited in the dark. That light has only just reached us. And the place it came from, it is no longer where we see it. It has moved. It is still moving. And in some cases it is moving away from us faster than light itself can follow. By the end of tonight, you are going to understand exactly why the universe has an edge you can never touch. A boundary that expands faster than any ship or signal could ever chase. And why that single fact is one of the most quietly devastating and wonder-filled truths in all of science. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. There was a night somewhere in your past when you looked up at the sky and felt it. That feeling is almost impossible to describe to someone who has never had it, but you know exactly what I mean. It is not quite wonder, and it is not quite fear. It is something in between. A sudden, vertiginous sense that the world beneath your feet is very small, and that the darkness above you goes on in ways your mind cannot fully hold. You stood there. Or maybe you were lying in the grass or leaning out a window, and for just a moment, the usual noise of your life went quiet. And the sky opened. Most of us had that moment when we were young, before the weight of schedules and responsibilities settled in, before we learned to keep our eyes at eye level and move through the world without looking up. Children look up constantly. They notice the moon in the afternoon sky. They ask why the stars do not fall. They want to know what is on the other side of the dark. And then slowly the world teaches them to stop asking. The questions get too big, and there are no satisfying answers, so we let them go. We file them somewhere in the back of our minds under things I will think about someday, and someday rarely comes. But tonight, someday is here. Tonight, you have given yourself permission to lie back, close your eyes if you want to, and let the questions come back. No pressure to solve them, no exam at the end. Just the slow, quiet pleasure of sitting with the biggest ideas the human mind has ever tried to hold. Because there is something genuinely extraordinary about what we're going to explore together over the next few hours. Something that took humanity thousands of years of looking up to finally understand. And something that, even now in the age of space telescopes and supercomputers and quantum physics, still manages to stop scientists in their tracks when they think about it too carefully. The universe has an edge. Or something very much like one, a boundary beyond which we cannot see, cannot send signals, and cannot ever travel, not because of any limitation in our technology, but because of the deep structure of reality itself. The laws of physics, the speed of light, the age of time, the expansion of space, all of these things conspire together to draw a circle around us, a cosmic horizon, and we sit at the centre of it, not because we're special, but because every point in the universe sits at the centre of its own horizon. That fact alone should give you pause. It is one of those ideas that sounds almost manageable the first time you hear it, and then, a few seconds later, quietly unravel something in your understanding of what the universe is. Here is the thing most people do not realise. When we talk about the edge of the universe, we are not talking about a wall. We are not talking about a place where space simply stops, like the edge of a table, with nothing on the other side. What we're talking about is a limit defined entirely by time and light. The universe is approximately 13.8 billion years old. That means light has had 13.8 billion years to travel from any given point and reach our eyes. Anything farther away than the distance light could cover in that time is, by definition, invisible to us. Not hidden behind something, not blocked, simply unreachable by the only messenger fast enough to cross the void, light itself. And yet, and this is where it gets genuinely strange, the edge of what we can see is not 13.8 billion light-years away. It is approximately 46 billion light-years away. Pause on that for a moment. If the universe is only 13.8 billion years old, how can we see things that are 46 billion light-years distant? That is more than 3 times farther than light should have been able to travel. The answer to that question is one of the most disorienting facts in all of modern science, and we are going to work through it together, gently, step by step, over the course of tonight. But I want you to feel that number first. 46 billion light-years, in every direction. That is the size of the sphere of space we can observe, and it is almost certainly not the size of the universe itself. Close your eyes for a moment and try to picture it. You're here, on this small rocky planet, orbiting an unremarkable star in the outer arm of a galaxy, containing somewhere between 100 billion and 400 billion other stars. That galaxy, our Milky Way, is one of at least 2 trillion galaxies in the observable universe. 2 trillion. A number so large it stops meaning anything to the human brain almost immediately. Each of those galaxies contains hundreds of billions of stars. Each of those stars may have planets, and all of that, all of it, exists within the bubble of space we can see. The bubble defined by the speed of light and the age of time. And beyond that bubble, we do not know. We genuinely do not know. It may be more of the same, stretching on forever. It may be something else entirely, or it may be something for which we do not yet have words. That is what tonight is about. Not just the distances, though the distances alone are enough to fill a lifetime of wonder. It is about what those distances mean, what they reveal about the nature of space and time and light, what they tell us about our place in a cosmos that is, by any honest measure, almost incomprehensibly vast, and what they quietly suggest about the limits of human knowledge, the places where our maps end and the unknown begins. I find something deeply comforting about that, even though on the surface it sounds terrifying. There is a strange peace in accepting how much we do not and cannot know, in sitting at the edge of understanding and simply looking out. I want to be your guide tonight, not a textbook, not a lecture. Think of me as someone sitting beside you in the dark, pointing up at the stars and saying, "Let me tell you what I know about how far away that is, and let me be honest with you about how much of it still keeps scientists awake at night." Because the distance to the edge of the universe is not just a number, it is a story about light and time and the expanding fabric of space itself. A story that begins 13.8 billion years ago in a moment of unimaginable heat and brightness. And that is still unfolding right now, in every direction, faster than we can follow. So settle in. Let your body relax into wherever you are right now. Let your breathing slow down. Tonight, we're going to travel as far as the human mind has ever traveled. We're going to push right up to the boundary of the observable universe and look out over the edge. And what we find there is going to be strange and humbling and vast and quietly, beautifully terrifying in the best possible way. The night sky is waiting. The edge of everything is out there, and we are just getting started. Before we go any further, I want to make sure we are both talking about the same thing, because the word universe gets used in a way that quietly glosses over one of the most important distinctions in all of cosmology, a distinction that, once you understand it, changes the entire shape of the question we're asking tonight. When most people say the universe, they mean everything. All of space, all of matter, all of energy, all of time, the totality of existence. And that is a perfectly reasonable way to use the word, but scientists have had to introduce a more careful term because it turns out that everything and everything we can see are 2 very different things. The term they use is the observable universe, and the gap between those 2 concepts is where tonight's deepest mystery lives. The observable universe is not the universe. It is a sphere, centered on you, centered on Earth, centered on wherever you happen to be standing or lying right now. that contains everything from which light has had enough time to reach us since the beginning of time. Think of it like a bubble. You're at the center of this bubble, and the walls of the bubble represent the farthest distance any light could have traveled since the universe began, roughly 13.8 billion years ago. Everything inside the bubble is, in principle, visible to us if we have a powerful enough telescope. Everything outside the bubble is, at least for now, completely beyond our reach. Not hidden, not blocked, simply not yet arrived. The light from those regions has been travelling toward us, but it has not had enough time to get here yet. The universe is young, cosmically speaking, and the messengers are still in transit. Now here is where it gets interesting. The observable universe is not a fixed thing. It is not a permanent wall. As time passes, light from more distant regions continues to arrive, and the observable universe slowly grows. Every second that ticks by, the sphere of space we can in principle observe expands a little further. You might think that means we will eventually be able to see everything, that given enough time, light from every corner of the cosmos will eventually reach us. And that is exactly what scientists once assumed. But we now know that is not true, and the reason why is one of the central revelations we will spend tonight unpacking. For now, just hold on to the image of the bubble, you at the center, light streaming in from every direction, and a horizon where your vision ends. Light is the key to all of this. I want you to really sit with that for a moment, because it is so fundamental that it is easy to take for granted and miss how strange it actually is. We do not see objects. We see light that has bounced off objects, or light that objects emit, and that light has to travel across space to reach our eyes. That travel takes time. When you look at a candle across a room, the light you see left that flame a fraction of a nanosecond ago, so small a delay that it is completely irrelevant. But when you look at the moon, you are seeing it as it was about 1.3 seconds ago. When you look at the sun, you are seeing it as it was approximately 8 minutes ago. When you look at Mars at its closest approach, you are seeing it as it was somewhere between 3 and 22 minutes ago, depending on where both planets are in their orbits. The further away something is, the older the image you're seeing. This is not a limitation of our instruments. It is a fundamental feature of how information travels through the universe. Nothing, no signal, no particle, no force, moves faster than light. And light, despite being the fastest thing in existence, still takes real, measurable time to cross real distances. So every telescope, in a profound sense, is also a time machine. When we point a telescope at a distant galaxy and capture its light, we are not seeing that galaxy as it is now. We are seeing it as it was when that light first departed, perhaps millions or billions of years ago. The galaxy we observe and the galaxy that actually exists right now in that location are not the same object. One is a fossil of light. The other is a living, evolving thing that we have never seen and may never see. This has a consequence that most people find quietly astonishing when they first encounter it. The most distant objects we can observe, the galaxies and quasars near the edge of our observable bubble, are not showing us what the universe looks like now. They are showing us what the universe looked like when it was very young. When we look at a galaxy 13 billion light-years away, we are seeing light that left it 13 billion years ago, when the universe itself was less than 1 billion years old. Those early galaxies no longer look like that. Many of them have merged with other galaxies, changed shape, evolved beyond recognition. Some of the stars we see in those ancient images burned out billions of years before the Earth even formed. We are looking at ghosts, beautiful ancient ghosts, frozen in the light that finally made it to us after an unimaginable journey through the expanding dark. So when I say we are going to travel to the edge of the observable universe tonight, I want you to understand what kind of edge that is. It is not a physical boundary in space. It is a boundary in time. It is the furthest back we can look, and because space was smaller and denser in the past, looking further out and looking further back are the same thing. The universe, in a sense, has given us a natural telescope pointed at its own origins. Every direction we look is a window into a different era of cosmic history, and the very edge of the observable universe, the cosmic horizon, is a window into the first moments after the Big Bang itself, when the universe was a seething plasma of energy so hot and so dense that light could not travel freely through it at all. That boundary, the place where light was first able to travel freely, is called the surface of last scattering, and the light from that moment, stretched and cooled by 13.8 billion years of cosmic expansion, is still reaching us today. We call it the cosmic microwave background, and it fills the entire sky in every direction, a faint whisper of ancient heat that our instruments can detect if they are sensitive enough. It is the oldest light in the universe. It is the closest thing we have to a photograph of the universe in its infancy, and it marks the absolute limit of what any telescope, no matter how powerful, will ever be able to show us about the early cosmos. Beyond that surface of last scattering, the universe is opaque to light. Whatever happened before that moment is hidden from us, perhaps permanently. But here is what I find extraordinary about all of this. The fact that we are limited, that we live inside a bubble of observable space, that we see only ancient light, that our knowledge of the universe has a horizon, does not diminish the universe. It does not make it less real or less magnificent. If anything, it deepens the wonder. Because we are a species that evolved on a small planet around a medium-sized star, with eyes designed to see fruit in trees and faces in firelight. And yet somehow, with those same eyes, and the instruments we built with our curious hands, we have mapped a sphere of space 93 billion light-years across. We have decoded light that is almost as old as time. We have learned the age and the shape and the composition of the cosmos we live in. That is not a small thing. That is, I think, one of the most astonishing things any mind has ever done. Let me give you a number. 186,000 miles per second. That is the speed of light in a vacuum. Take a moment to let that sink in, not just as a piece of trivia, but as something you actually try to feel. 186,000 miles in a single second. The circumference of the Earth is roughly 24,900 miles, which means that in 1 second, a beam of light could circle our entire planet approximately 7.5 times. 7.5 laps around the Earth while you blink. It is the fastest thing in the universe. It is, as far as we know, the fastest thing that can ever exist. And tonight, I want to show you why that extraordinary speed, a speed so vast it makes every human achievement in transportation look like a crawl, is still nowhere near fast enough to cross the universe in any meaningful way. The speed of light is not just a physical constant, it is a cosmic speed limit, built into the architecture of reality itself. Albert Einstein showed us this in 1905 in his special theory of relativity. The closer any object with mass gets to the speed of light, the more energy it requires to accelerate further. Not linearly, exponentially. As you approach the speed of light, the energy required approaches infinity, which means that nothing with mass, no ship, no probe, no human body, can ever actually reach it. Light itself can travel at that speed because photons, the particles of light, have no mass at all. They are pure energy, and they move at the maximum speed the universe permits from the very moment they are created. For everything else, that speed is a wall you can approach but never touch. We are, all of us, permanently slower than light, and in a universe as large as ours that matters enormously. Now let us use that speed to take a short tour of our cosmic neighbourhood, just to calibrate your sense of scale before we start talking about billions of light years. The Moon is about 239,000 miles away from Earth on average. At the speed of light, you could get there in roughly 1.3 seconds. That feels manageable. Now let's go to Mars. At its closest approach to Earth, Mars is about 34 million miles away. Light covers that distance in about 3 minutes, still not too frightening. But now let's go to the edge of our solar system, to the region where the Voyager 1 probe is currently travelling, more than 14 billion miles from the Sun. Light takes about 22 hours to reach that distance, 22 hours travelling at 186,000 miles per second, and Voyager 1 has been flying since 1977. The solar system alone begins to feel enormous. Now step outside it. The nearest star to our Sun is Proxima Centauri, roughly 4.2 light-years away. That means light, travelling at its maximum speed, takes 4.2 years to cover that distance. If we sent the fastest spacecraft humanity has ever built, the Parker Solar Probe, which at its peak reaches about 430,000 miles per hour, it would take approximately 6,900 years to reach Proxima Centauri. 6,900 years. When that journey began, the ancient Egyptians would not yet have built the pyramids. That is the nearest star, the very next one. and already the numbers have left the realm of anything our lives can contain. This is what I mean when I say the arithmetic of space is cruel. It does not scale the way our intuitions expect it to. Every step outward is not just bigger, it is a different category of large. The Milky Way galaxy, our home, is approximately 100,000 light-years across. To travel from one side to the other at the speed of light would take 100,000 years. Not 100,000 years of travel time from our perspective, with some relativistic time compression helping us along. 100,000 years as measured by the universe, by the stars, by the clocks of any civilization waiting at the destination. Our galaxy is so large that light itself, the fastest thing there is, would need longer than our entire recorded human history multiplied by many times over just to cross it. And the Milky Way is not a particularly large galaxy. There are galaxies in the observable universe that dwarf ours by a factor of 10 or 20 or more. Beyond the Milky Way, the distances grow so fast that the human mind genuinely starts to short-circuit trying to hold them. The Andromeda Galaxy, our nearest large galactic neighbour, is about 2.5 million light-years away. That means the light entering your eyes if you looked at Andromeda on a clear dark night left that galaxy 2.5 million years ago. At that time our ancestors were early hominins walking the African savanna, not yet fully human in the way we understand ourselves today. The universe we see in Andromeda's direction is a universe from before the human story even properly began. And Andromeda is, cosmically speaking, right next door. It is practically touching us. The observable universe extends roughly 46 billion light-years in every direction. Andromeda at 2.5 million light-years is less than a fraction of a percent of that total reach. Here is the thing most people do not realize when they first absorb these numbers. The speed of light, for all its magnificence, is in some ways a cruel joke that the universe plays on anything curious enough to want to explore it. The universe is so vast, and the speed limit so comparatively slow, that even if we somehow solved every engineering problem, even if we built ships that could travel at the full speed of light which physics forbids, we still could not explore more than the tiniest corner of what exists. In a human lifetime, travelling at light speed, you could reach stars within perhaps 80 or 90 light-years of Earth. Sounds like a lot, until you remember that the Milky Way alone is 100,000 light-years across, and there are 2 trillion galaxies beyond ours. The universe is not just large, it is large in a way specifically designed, if such a word even applies, to be unreachable. And yet here we are, reaching for it anyway, with telescopes instead of ships, with mathematics instead of engines, with light itself as our only messenger, carrying information across distances that no physical thing could ever cross in any useful span of time. There is something both humbling and heroic about that. We are creatures of a pale blue dot, pinned to the surface of a rock by gravity, unable to travel faster than a tiny fraction of the speed of light. And we have still managed to map a universe 46 billion light-years across. We did it by being patient, by being clever, by learning to read the light that the cosmos sends us and understanding what it means. That is what science is, at its heart. Not conquest, not domination, just listening, very carefully, to the messages that light carries across the dark. And tonight, you and I are listening together to the most astonishing message of all, the story of how far away everything really is and what that distance truly means. Imagine standing in the middle of a vast flat plain in the middle of the night. In every direction, the land stretches away from you, into the darkness. You cannot see where it ends, you cannot see how far it goes. But there is a horizon, a circle around you defined not by where the land stops, but by the limits of your own vision. Beyond that horizon, the plain almost certainly continues. There is more out there, but you cannot see it from where you stand. Now imagine that the plain is space itself, stretching in 3 dimensions in every direction rather than 2. And imagine that your horizon is not defined by the curvature of the Earth, but by the speed of light and the age of the universe. That circle around you, that boundary of what you can in principle observe, is what cosmologists call the observable universe. And tonight I want to walk you right up to the edge of it and let you look over. The observable universe is a sphere approximately 93 billion light-years in diameter. You are at the centre, not because Earth is special, not because we occupy some privileged position in the cosmos, but because the observable universe is defined entirely by what any given observer can see, and you are the observer tonight. Every point in the universe has its own observable bubble centered on itself, each one slightly different depending on that point's location and history. The bubbles overlap enormously, but no two are identical. A civilization in a galaxy 10 billion light-years from here has its own horizon, its own bubble, and sees a universe that partially overlaps with ours but extends into regions we will never observe. We each carry our own cosmic horizon with us, invisible and absolute wherever we go. Now the number I gave you, 93 billion light-years across, needs some explaining, because it seems to contradict something I told you earlier. The universe is 13.8 billion years old. If light has been travelling for 13.8 billion years, how can anything be 93 billion light-years away? That number is more than 6 times larger than the age of the universe in light-years. If light can only travel 13.8 billion light-years in 13.8 billion years, how can we see objects that are now 46 billion light-years away? This is the question that sits at the heart of tonight's mystery, and the answer, when you really absorb it, is one of the most mind-bending facts in modern cosmology. The universe, you see, has not been sitting still. Space itself has been expanding, not like an explosion where objects fly outward through space. Rather, the fabric of space itself, the medium through which everything moves, has been stretching, like dots painted on the surface of a balloon that is being inflated. The dots do not move across the surface, but the distances between them grow as the rubber stretches. This means that two galaxies can be moving apart from each other, even if neither of them is moving through space at all. The space between them is simply growing. And this changes everything about how we measure cosmic distances. When the light that is now reaching us from the most distant observable galaxies first left those galaxies, they were much closer to us than they are now. But in the billions of years that light has been travelling toward us, space has expanded enormously, carrying those source galaxies much farther away. By the time their light arrives, its point of origin has moved to a distance far greater than the light itself has travelled. This is why the edge of the observable universe, the cosmic horizon, sits at 46 billion light-years rather than 13.8 billion. The light reaching us from that horizon left its source when the universe was very young, and those regions were much closer. But space has stretched so dramatically in the intervening billions of years that those regions are now 46 billion light-years away. The light made a 13.8 billion light-year journey, but the destination has moved more than 3 times as far as the journey itself. If you have ever walked toward a point on a moving walkway that is itself sliding away from you, and found that you are covering ground but the destination seems to recede, you have a small intuitive taste of what light experiences crossing an expanding universe. Except in the cosmic case, the walkway is all of space, and it stretches in every direction simultaneously. Here is what the edge of our observable bubble actually looks like, in the most literal sense we can describe. In the early universe, for the first roughly 380,000 years after the Big Bang, the cosmos was so hot and so dense that it was opaque. Light could not travel freely through it. Photons were constantly colliding with charged particles, absorbed and re-emitted almost immediately, unable to get anywhere. The early universe was like the interior of a star, brilliant with energy but utterly foggy. Then, as the universe expanded and cooled to roughly 3,000 degrees, something changed. Electrons and protons combined to form neutral hydrogen atoms for the first time. Suddenly the fog cleared. Light was free to travel. The universe became transparent, and that moment, called recombination, is the wall we see when we look to the very edge of our observable bubble. It is not a wall of space, it is a wall of time. The moment before which the universe was opaque to us forever. The light from that moment of clearing is still washing over us today. It has been travelling for 13.8 billion years, cooling and stretching as space expanded, until its wavelength has been pushed far beyond visible light into the microwave range. We call it the cosmic microwave background, and it is detectable in every direction of the sky with the right instruments. It is the oldest light we can ever hope to observe, and it defines the hard outer shell of our observable universe. Beyond it, in the direction of even earlier times, the universe is permanently hidden from us, not by distance alone, by the physics of how light and matter interacted in the first moments of cosmic history. The horizon is not just far, it is sealed. I want you to hold the full picture in your mind for a moment. You, here, at the center of a bubble 93 billion light-years across. Inside that bubble, 2 trillion galaxies, each containing hundreds of billions of stars, spread across cosmic filaments and voids in a web of almost incomprehensible complexity. Around the outside of that bubble, a faint glow of ancient microwave light, the echo of the universe's first transparency, imprinted 13.8 billion years ago. And beyond that glow, more universe, almost certainly far more, that we cannot see and may never be able to see, not because space ends, but because light has not had time to reach us, and in some regions never will. Our cosmic bubble is not a cage, it is more like a shoreline. Behind us is everything we know, ahead is an ocean with no visible far shore, and the tide of light keeps bringing new information in, slowly, one photon at a time, across the vast and patient dark. The year was 1929. An astronomer named Edwin Hubble was working at the Mount Wilson Observatory in the mountains above Los Angeles, using what was at the time the most powerful telescope on Earth. He had spent years carefully measuring the light coming from distant galaxies, objects that, until just a few years earlier, most scientists had believed were simply clouds of gas within our own Milky Way. Hubble had already proven they were not. They were entire separate galaxies, island universes in their own right, each containing hundreds of billions of stars. That discovery alone had already remade humanity's picture of the cosmos. But what Hubble found next was something nobody had expected, something that would unsettle every assumption about the nature of the universe and launch a chain of discoveries that continues to astonish us to this day. Hubble noticed something strange in the light from those distant galaxies. The light was shifted, not randomly, not inconsistently, but in a very specific and systematic way. The light from almost every galaxy he studied was redder than it should have been, and the farther away a galaxy was, the redder its light appeared. This phenomenon is called redshift, and it works on the same principle as the familiar change in pitch you hear when an ambulance passes you on the street, what physicists call the Doppler effect. When a source of waves is moving away from you, the waves get stretched. For sound, that means a lower pitch. For light, it means a shift toward the red end of the spectrum. What Hubble was seeing, written in the colour of starlight, was that almost every galaxy in the sky was moving away from us. Not just a few, not just the distant ones, almost all of them, in almost every direction, receding into the dark. The simplest interpretation of this discovery would be that we are at the centre of some kind of cosmic explosion, with everything flying outward from a central point where we happen to sit. But that interpretation turned out to be wrong, or at least profoundly incomplete. The key insight, the one that took cosmologists a few years to fully absorb, was that the recession of the galaxies was not because they were moving through space away from us. It was because the space between us and them was expanding. There is a crucial difference. If galaxies were simply flying away from a central point, then from any other galaxy in the universe, you would see a different pattern. Some galaxies coming toward you, others going away, depending on your position relative to the centre. But what Hubble found is true from everywhere. Every galaxy sees every other galaxy receding. There is no centre. There is no edge from which things fly outward. Space itself is simply getting bigger, everywhere, all at once. The analogy that helps most people is the raisin bread analogy, and I want to give it to you slowly because it really does carry the idea well. Imagine a loaf of raisin bread before it goes into the oven. The raisins are distributed throughout the dough, some close together, some farther apart. Now the bread goes in, and the dough begins to rise and expand. As it does, every raisin moves away from every other raisin, not because the raisins are moving through the dough, but because the dough between them is growing. A raisin that is close to another raisin sees its neighbour move away slowly, but a raisin that is far from another raisin sees it move away much more quickly, because there is more expanding dough between them. Now replace the raisins with galaxies, and the dough with space itself, and you have a remarkably accurate picture of what Hubble discovered. The universe is the loaf, and it has been rising since the very beginning. This expansion carries a staggering implication that Hubble himself recognized almost immediately. If everything is moving apart from everything else right now, then working backward in time, everything must have once been closer together. Much closer. Rewind the expansion far enough, and all the matter and energy in the observable universe converges to a single point of unimaginable density and temperature. A beginning, a moment before which the concepts of space and time as we understand them may not even apply. We call that moment the Big Bang, and it happened approximately 13.8 billion years ago. The expansion Hubble observed is not the aftermath of an explosion in space. It is the expansion of space itself continuing from that primordial beginning, carrying everything in the universe along with it like raisins in an eternally rising loaf. Now here is where the story takes a turn that even Hubble could not have anticipated, because the expansion he discovered was only the beginning of a stranger truth. For decades after his discovery, cosmologists assumed the expansion was slowing down. This seemed like common sense. Gravity is a universal attractive force. All the matter in the universe pulls on all the other matter, so while the universe is expanding outward from the Big Bang, gravity should be acting as a brake, gradually slowing that expansion over time. The question scientists were asking was not whether the expansion was slowing, but whether it was slowing enough to eventually stop and reverse, to one day pull everything back together in what they called the Big Crunch. That was the picture most cosmologists held going into the 1990s. Expansion, yes, but decelerating expansion headed toward an eventual end. What they found instead in 1998 was so unexpected that it earned the scientists who discovered it a Nobel Prize. Two independent teams of astronomers studying a specific type of exploding star called a Type Ia supernova, which functions as a reliable cosmic measuring stick because it always explodes with nearly the same intrinsic brightness, found that the most distant supernova were dimmer than expected. Not brighter, dimmer, which meant they were farther away than they should be if the expansion was slowing down. The universe was not decelerating, it was accelerating. The expansion of space was not being reined in by gravity. It was speeding up. Something was pushing space apart faster and faster with every passing moment, something that had no name, no clear identity, and no precedent in the physics anyone had written down. They called it dark energy, and it remains one of the deepest unsolved mysteries in all of science. What this means for our story tonight, for the question of the edge of the universe and what lies beyond, is profound and a little terrifying. Because if the expansion of space is accelerating, then the most distant galaxies we can currently see are not merely moving away from us. They are moving away from us at an ever-increasing rate. Each day that passes, each year, each millennium, more and more of the universe crosses a threshold from which its light can never reach us again. The observable universe, rather than growing as time passes and more light arrives, will eventually begin to shrink in terms of the number of galaxies it contains. Galaxies that are currently visible to us will one day vanish beyond our horizon, their light stretched to infinity by the accelerating expansion, never to be recovered. The universe is not just large, it is actively, relentlessly growing larger in a way that is working against us. And that changes everything about what the edge of the universe really means. There is something in the universe that we cannot see, cannot touch, cannot measure directly, and cannot explain with any theory we currently possess. It has no mass. It emits no light. It does not interact with matter in any way we know how to detect. And yet it makes up approximately 68% of the total energy content of the entire universe. It is the dominant ingredient in the cosmic recipe. More than 2/3 of everything that exists in terms of energy is this mysterious, invisible something. We call it dark energy, not because it is dark in the way that darkness is an absence of light, but simply because we have no idea what it is. The name is a placeholder, a confession of ignorance dressed up in scientific language. And tonight, I want to sit with you in that ignorance for a while, because what dark energy does, even if we do not know what it is one of the most consequential and unsettling facts about the universe we inhabit. To understand dark energy, you need to go back to 1998 and two teams of astronomers who were racing to answer what seemed like a straightforward cosmological question. Everyone knew the universe was expanding. Hubble had established that in 1929. The question these teams were trying to answer was how fast the expansion was slowing down. Note the assumption buried in that question, not whether it was slowing. How fast? Gravity pulls matter together. The universe is full of matter. Therefore, the expansion must be decelerating. It was as close to a foregone conclusion as cosmology had. The two competing teams, the Supernova Cosmology Project and the High Z Supernova Search Team, were essentially trying to measure the breaks. What they found instead was that the breaks did not exist. The universe was not decelerating at all. It was accelerating. The expansion of space was getting faster, and when those results came in, the scientists on both teams spent a long time checking their data, convinced they had made an error. They had not made an error. The tool they used to make this discovery was a specific type of exploding star called a Type Ia supernova. These explosions are extraordinarily useful to cosmologists because they are remarkably consistent. When a white dwarf star, the dense remnant of a dead sun-like star, accumulates enough mass from a companion star to exceed a critical threshold, it explodes in a thermonuclear detonation of almost perfectly predictable brightness. Because we know how bright these explosions actually are, we can measure how bright they appear from Earth and calculate exactly how far away they are. They are, in the language of cosmology, standard candles, reliable markers of distance across cosmic scales, and when the two teams measured the distances to the most remote Type Ia supernovae ever observed, those supernovae were consistently farther away than the models predicted. Not by a small margin, by enough to overturn the entire prevailing picture of the universe's fate. The implication was inescapable. If the most distant supernovae were farther away than expected, it meant the universe had been expanding faster in the recent cosmic past than models of a decelerating universe would predict. Something was adding energy to the expansion. Something was pushing space apart with increasing force over time. The simplest way to account for it mathematically was to resurrect a term that Einstein himself had introduced into his equations of general relativity back in 1917, and then famously abandoned, a term he called the cosmological constant, which represented a kind of intrinsic energy of empty space itself. In Einstein's original formulation, he had used it to try to keep the universe static, believing at the time that the universe was neither expanding nor contracting. When Hubble proved the universe was expanding, Einstein reportedly called the cosmological constant his greatest blunder. In 1998, it turned out it was not a blunder at all, it was a prophecy. Here is what dark energy appears to do, described in the most concrete terms I can offer. Ordinary matter and energy, stars, galaxies, gas, radiation, everything you have ever seen or touched, dilutes as the universe expands. Pour the same amount of water into a larger and larger container, and the water gets thinner and thinner. Gravity weakens as matter spreads out. But dark energy does not dilute. As space expands and new space is created, dark energy fills that new space at the same density as before, which means that as the universe grows, the total amount of dark energy grows with it. And as the total amount of dark energy grows, its repulsive effect on the expansion of space grows stronger. The expansion accelerates, which creates more space, which creates more dark energy, which accelerates the expansion further. It is a runaway process, and it has been winning for roughly 5 billion years since dark energy's influence overtook that of matter. It is still winning now. It is winning faster every day. The current best measurements suggest that the universe's expansion is accelerating at a rate described by what cosmologists call the Hubble constant, though the exact value of this constant is itself the subject of one of the most heated debates in modern physics, a disagreement called the Hubble tension that has yet to be resolved. What we do know is that galaxies beyond a certain distance from us are already receding faster than the speed of light. This does not violate Einstein's cosmic speed limit, because those galaxies are not moving through space faster than light. It is the space between us and them that is expanding at that rate. Space itself is not subject to the speed of light, only things moving through space are. So when cosmologists say a distant galaxy is receding from us at faster than the speed of light due to cosmic expansion, they are not saying anything travels faster than light. They are saying the distance between us is growing faster than light can cross it. The distinction is technically important. Emotionally, it is terrifying either way. What does dark energy feel like if you could somehow sense it? Nothing. Absolutely nothing. It is present in the room where you're lying right now. It is present in the space between the atoms of your body. It is present in the void between galaxies and in the vast cosmic emptiness between galaxy clusters. It is everywhere, at all times, at the same density, exerting its quiet, relentless outward pressure on the fabric of space. and it is completely imperceptible to any human sense or any instrument we have built, except through its gravitational effects on the large-scale structure of the universe. We know it is there only because the universe is behaving in a way that cannot be explained without it. It is defined entirely by what it does, with no understanding yet of what it is. Some physicists think it is the energy of the quantum vacuum, the seething, roiling energy of empty space itself, predicted by quantum mechanics. Others think it is something else entirely, something that requires new physics we have not yet discovered. What I find most remarkable about dark energy, and most quietly humbling, is what it says about the limits of our knowledge. We have spent centuries learning to see the universe more and more clearly. We have built telescopes that can detect the light of the first galaxies. We have decoded the composition of stars from their spectra. We have mapped the large-scale structure of the cosmos in extraordinary detail, and yet the dominant ingredient in the universe, the force that is shaping the entire future of everything, remains almost completely opaque to us. We know it is there, we know what it does, we have given it a name, and beyond that, we are largely in the dark, in every sense of the word. That is not a failure of science. It is an honest acknowledgement of where the frontier lies, and frontiers, by definition, are where the most interesting things are waiting to be found. I want to tell you about a line. Not a physical line you could see or cross, not a line drawn on any map, but a boundary that exists in the fabric of space itself, as real and as absolute as any wall ever built. Scientists call it the cosmic event horizon, and what lies beyond it is, in the most precise and literal sense possible, forever beyond our reach, not beyond our reach with current technology, not beyond our reach for the next 1,000 years, forever, permanently, with no possibility of exception, no matter what we discover, no matter how advanced we become, no matter how long our civilization survives. The cosmic event horizon is the distance beyond which the expansion of space is carrying galaxies away from us faster than light can travel, and anything beyond that line, any galaxy, any star, any signal, can never reach us. Not today, not in 1 billion years, not ever. To feel the full weight of this, I want you to think carefully about what it means for something to recede faster than light. We established earlier that space itself is not bound by the cosmic speed limit. Only things moving through space face that restriction. Space can expand at any rate, and in the regions far enough from us it does expand faster than light travels. Right now, as you lie here in the dark, there are galaxies in the observable universe, galaxies whose light is currently reaching our telescopes, whose locations are receding from us faster than the speed of light. We can see them, because the light they emitted long ago, when they were closer to us, has been travelling toward us for billions of years and has finally arrived. But the galaxies themselves, the physical objects, are now so far away that space between us and them is growing faster than any new light they emit could ever cross. We are seeing their past. Their present is already beyond our horizon, and their future will never reach us at all. Here is where it becomes genuinely difficult to sit with, and I want to give you a moment to really absorb it. Imagine a galaxy, let us call it Galaxy A, that is currently right at the edge of the cosmic event horizon. Light emitted by Galaxy A today, at this very moment, is travelling toward us at the speed of light. But the space between us and Galaxy A is expanding at exactly the speed of light. So that light is, in a sense, running on a treadmill. It moves toward us at full speed, but the ground beneath it expands at the same rate. It makes no progress. It hangs there, frozen at the same distance from us indefinitely, unable to advance and unable to retreat. Now move Galaxy A just a little further away, just beyond that critical threshold. The space between us expands faster than light can travel. The light it emits today will never reach us. It will recede from us forever, moving away into an ever-deepening darkness, carrying its message to no one. The galaxy becomes, from our perspective, as if it never existed at all. The cosmic event horizon is currently estimated to be approximately 16 billion light-years away from us. Not 46 billion, which is the edge of the observable universe, the limit defined by how far light has travelled since the Big Bang. The event horizon is closer. It is the distance beyond which the expansion of space is already winning against light, right now, in the present moment. Everything between 16 billion and 46 billion light-years from us is currently visible to us. We can see light that left those regions long ago. but those regions themselves are already receding faster than light. We are seeing their ancient past. Their present and future are lost to us, and as dark energy continues to accelerate the expansion of space, that event horizon will shrink further over cosmic time, pulling more and more of the currently observable universe beyond our permanent reach. Let me give you a number that I find more quietly devastating than almost any other in cosmology. There are an estimated 2 trillion galaxies in the observable universe. 2 trillion. An almost incomprehensible abundance of island universes, each containing hundreds of billions of stars, each potentially harboring planets, chemistry, complexity, perhaps even minds looking back at us across the dark. Of those 2 trillion galaxies, the vast majority are already beyond our cosmic event horizon, already receding faster than light, already permanently unreachable by any ship, any signal, any message we could ever send. The galaxies within our event horizon, the ones we could theoretically reach if we travelled at the speed of light, which we cannot, represent only a small fraction of what we can see. Most of what we observe in our telescopes is already gone from us in every meaningful sense. We see it. We can never touch it. There is something I want to name here, because I think it deserves to be named clearly. This is not a problem that technology will solve. This is not a challenge that a sufficiently advanced civilization will overcome given enough time. The cosmic event horizon is not like the sound barrier, which seemed insurmountable and turned out not to be. It is not like the distance to the moon, which seemed unreachable until we built rockets. The event horizon is a fundamental consequence of the structure of space-time and the behavior of dark energy. If dark energy continues to behave the way it currently does, and every observation we have suggests it will, then the most powerful civilization imaginable, given unlimited time and unlimited resources, could still never reach a galaxy that is today beyond that horizon. The universe has drawn a line around us with the ink of physics itself, and that line is not a challenge. It is a permanent condition. And yet, and I want to hold this thought carefully because I think it matters, there is something worth noticing about the fact that we know this. We're a species that has existed for perhaps 300,000 years on a small rocky planet orbiting an ordinary star. We have had writing for roughly 5,000 years, and modern science for perhaps 400. And in that extraordinarily brief window, we have figured out not only that the universe is expanding, but that it is accelerating, and that there is a horizon beyond which nothing can ever reach us, and approximately where that horizon lies, and what it means for the long-term future of everything we can observe. We cannot cross that horizon, but we found it, we mapped it, we understood it, and there is a kind of defiant wonder in that, in the fact that minds made of star stuff, living on a mote of dust, have looked out into the expanding dark and traced the boundaries of the reachable universe with mathematics and light. So tonight, when you think about the galaxies we will never reach, I want you to hold 2 things at once. The first is the genuine weight of it, the scale of what is forever beyond us, the humbling reminder that the universe is under no obligation to be accessible to us, and that the cosmic event horizon represents a kind of absolute limit on the human story as we currently understand it. The second is the quieter, stranger comfort of knowing that within our horizon, within the bubble of space that light can still cross and signals can still traverse, there is more wonder than any civilization could exhaust in any span of time we can imagine. 2 trillion galaxies may lie beyond our reach, but the ones within it number in the hundreds of billions. The universe has not left us with nothing. It has left us with more than enough. It has left us with a lifetime of looking up. When most of us picture the universe, we picture galaxies, bright spinning islands of stars scattered across the dark like embers from a fire. And that picture is not wrong, exactly. But it is incomplete in a way that becomes staggering the moment you zoom out far enough. Because galaxies, for all their magnificence, are not the largest things in the universe. They are not even close. Galaxies are, in the architecture of the cosmos, something like individual bricks. And what those bricks build, the structures they form when you pull back far enough to see the whole, is something so vast, so intricate, and so alien in its scale that it makes individual galaxies feel like atoms in comparison. Tonight I want to take you on a journey upward through the layers of cosmic structure, from galaxies to clusters to superclusters to the largest things that have ever existed, and I want you to feel each step of that ascent in your bones. Let us start with something familiar. The Milky Way is a large spiral galaxy containing somewhere between 100 billion and 400 billion stars. It is roughly 100,000 light-years across. Impressive by any human standard. But the Milky Way does not travel alone. It is gravitationally bound to a collection of several dozen other galaxies, some large, most small, in what astronomers call the local group. The local group spans roughly 10 million light-years. It includes the Andromeda Galaxy, the two Magellanic Clouds, and a scattering of smaller dwarf galaxies orbiting the larger ones like satellites. From the outside, if something could see the local group whole, it would look like a small, loose cluster of glowing patches suspended in a much larger darkness. Cozy, almost, by cosmic standards. A small neighbourhood at the end of a very long road. But the local group is itself just one small node in a much larger structure. Our galactic neighbourhood is part of the Virgo supercluster, a vast collection of galaxy groups and clusters spread across approximately 110 million light-years. The Virgo supercluster contains somewhere in the range of 100 galaxy groups and clusters, including our own local group, all loosely connected by gravity into a flattened, irregular shape that astronomers have mapped in considerable detail. For decades, the Virgo supercluster was considered one of the primary large-scale structures of the universe, a major player in the cosmic architecture. Then, in 2014, a team of astronomers led by Brent Tully at the University of Hawaii redrew the map entirely. They discovered that the Virgo supercluster is not a freestanding structure at all. It is just one lobe of something enormously larger. They called it Laniakea, a Hawaiian word meaning immeasurable heaven, and Laniakea is 500 million light-years across, containing the mass of 100 million billion suns, encompassing 100,000 galaxies. The Milky Way is one of them, a single point in a structure so large that light would take 500 million years to cross it. And even Laniakea is not the end of the story. Zoom out further, and the superclusters themselves, Laniakea, the Perseus-Pisces supercluster, the Coma supercluster, and hundreds of others, are arranged in a pattern that no one anticipated before the large-scale surveys of the universe began in earnest in the 1980s and 90s. That pattern is called the cosmic web. It is one of the most beautiful and most humbling things humanity has ever mapped. The galaxies in the universe are not distributed randomly or uniformly. They are arranged in long, thin filaments, threads of matter hundreds of millions of light-years long, that connect at dense nodes where galaxy clusters pile up. Between those filaments are enormous empty regions called cosmic voids, where almost nothing exists, no galaxies, no clusters, just space, vast and cold and nearly empty, spanning hundreds of millions of light-years in every direction. The cosmic web looks, when you see it rendered on a computer screen from cosmological survey data, startlingly like a neural network, like the inside of a brain, long fibers connecting at nodes, surrounded by open space. The resemblance is purely structural and entirely coincidental, and yet it stops people every time. The filaments of the cosmic web contain some of the largest discrete structures ever identified. The Sloan Great Wall, discovered in 2003 using data from the Sloan Digital Sky Survey, is a filament of galaxies approximately 1.4 billion light-years long. When it was discovered, it was the largest known structure in the universe. It held that title for about 8 years. Then, in 2011, astronomers identified the Huge Large Quasar Group, a collection of quasars, which are extraordinarily luminous galactic cores powered by supermassive black holes, spanning approximately 4 billion light-years. For a brief time, that was the largest known structure. It too was surpassed. In 2013, a gamma-ray burst clustering known as the Hercules Corona Borealis Great Wall was identified. Current estimates suggest it spans approximately 10 billion light-years. 10 billion light-years. That is more than 1/10 the diameter of the entire observable universe. A single structure, a single connected filament of matter and energy that stretches across 1/10 of everything we can see. Here is the thing most people do not realize about structures at this scale. There is actually a theoretical limit to how large a coherent cosmic structure should be able to grow. In a universe governed by the cosmological principle, the idea that the universe is broadly uniform and homogeneous when viewed at large enough scales, structures above a certain size should not exist, because the universe has not had enough time for gravity to build them. That limit is generally placed at somewhere around 1.2 billion light-years. The Hercules Corona Borealis Great Wall, at 10 billion light-years, is roughly 8 times larger than that theoretical maximum. Its existence is, in the strict scientific sense, something that current models of cosmic structure formation struggle to fully explain. It should not be as large as it is, and yet there it is, spread across 10 billion light-years of sky, quietly defying our expectations of how the universe is supposed to behave. I want to use this moment to give you a sense of what travelling through the cosmic web would feel like if you could somehow compress the distances into something traversable. You would start in a galaxy cluster, a dense, bright knot of hundreds or thousands of galaxies packed into a relatively small region, surrounded by hot gas glowing in X-rays. Moving outward from the cluster, you would enter a filament, a long river of galaxies and dark matter stretching across hundreds of millions of light-years, the matter flowing slowly along it under the influence of gravity toward the dense nodes at each end. Crossing the filament, you would enter a void, and here the experience would change completely. The galaxies would thin out, then become rare, then almost entirely disappear. You would be in a vast, cold, nearly empty expanse of space, where a galaxy might be hundreds of millions of light-years from its nearest neighbour. The silence, if silence could be felt, would be total, and you might travel for hundreds of millions of light-years through that emptiness before the faint glow of another filament begins to appear on the horizon ahead. This is the universe at its largest scales. Not a uniform fog of stars, not a random scatter of galaxies. An intricate, ancient architecture of filaments and voids, built over 13.8 billion years by the slow pull of gravity and the opposing push of dark energy, stretching from one end of the observable universe to the other in a web of almost inconceivable complexity. And we're here, on a small rocky world, in one galaxy among hundreds of billions, in one small corner of one filament, in one supercluster among thousands, looking out at all of it and trying to understand. There is something in that, in the sheer audacity of the attempt, that I find more moving than almost anything else I know. In 1964, 2 radio astronomers at Bell Telephone Laboratories in New Jersey were trying to build the most sensitive radio antenna in the world. Their names were Arno Penzias and Robert Wilson, and their goal was entirely practical. They wanted to map radio signals from the Milky Way with unprecedented precision for use in communications research. But no matter what they did, no matter how carefully they calibrated their equipment, no matter which direction they pointed their large horn-shaped antenna, they kept detecting a faint, persistent hiss, a low, uniform noise that refused to go away. It was present in every direction of the sky, at all hours of the day, in every season. They checked their equipment exhaustively. They recalibrated. They even found a pair of pigeons nesting inside the antenna and cleaned out what they diplomatically described as a white dielectric material, bird droppings, wondering if that might be the source of the interference. It was not. The hiss remained, soft, steady, and everywhere at once. What Penzias and Wilson had stumbled upon, without knowing it, was the oldest light in the universe, the literal echo of the Big Bang itself, still ringing across the sky nearly 14 billion years later. To understand what that hiss actually is, I need to take you back to the very early universe. In the first moments after the Big Bang, the cosmos was unimaginably hot and dense, not hot like a star, hot like the entire mass energy of everything that exists, compressed into a space smaller than an atom, temperatures in the trillions of degrees and beyond. In those conditions, matter as we know it could not exist. There were no atoms, no molecules, no structures of any kind, just a seething plasma of fundamental particles, quarks, electrons, photons, colliding and interacting constantly at energies so extreme that any particle that tried to form a stable bond was immediately ripped apart again. This plasma was opaque. Light could not travel through it freely. Photons were constantly absorbed and re-emitted, bouncing from particle to particle like light inside a frosted glass bulb, unable to get anywhere. The early universe was brilliant with energy and completely foggy at the same time. This state of affairs continued for approximately 380,000 years. 380,000 years of unimaginable heat, constant collision, and perfect opacity. And then something changed. The universe had been expanding and cooling steadily since the moment of its birth. By 380,000 years in, the temperature had dropped to roughly 3,000 degrees, still blazing hot by any earthly standard, but cool enough for a critical transition to occur. Electrons, which had been flying free in the plasma, began to slow down enough to be captured by protons. Hydrogen atoms formed for the first time, and as neutral hydrogen atoms replaced the charged plasma, the universe became suddenly dramatically transparent. Photons that had been trapped for 380,000 years were abruptly free to travel. They streamed outward in every direction, filling all of space with a wash of light. Cosmologists call this moment recombination, and the light released at that moment is what Penzias and Wilson detected in 1964, still travelling, still filling the sky, nearly 14 billion years later. Of course, those ancient photons do not look like visible light anymore. When they were first released, they had a temperature of about 3,000 degrees, glowing a dull orange red, something like the surface of a very cool star. But in the billions of years since, the universe has expanded enormously, and that expansion has stretched the wavelength of those photons along with it. The more a photon's wavelength is stretched, the lower its energy and the lower its equivalent temperature. Today, after 13.8 billion years of cosmic expansion, those once orange photons have been stretched all the way into the microwave range of the electromagnetic spectrum, far beyond what human eyes can see. Their equivalent temperature today is just 2.7 degrees above absolute zero, 2.7 Kelvin. The faintest whisper of warmth spread uniformly across the entire sky in every direction. This is what Penzias and Wilson were hearing. This is what their antenna detected. The stretched, cooled, ancient light of the universe's first moment of transparency, arriving at Earth after a journey of nearly 14 billion years. The cosmic microwave background, or the CMB, is the most distant thing we can ever observe. It is not a place. It is a moment in time, projected onto the sky in every direction. When you look toward the CMB, you're looking as far back in time as it is possible to look using light. You're seeing the universe as it was 380,000 years after its birth, before any stars had formed, before any galaxies existed, before any of the structure we see in the universe today had begun to take shape. It is a snapshot of the early cosmos in its simplest, most primordial state, and it is, in a sense, the wall at the back of our observable universe. Beyond it, in terms of both distance and time, the universe is opaque to us. Whatever happened in the first 380,000 years, the processes of the Big Bang itself, inflation, the formation of the first particles, is permanently hidden behind this curtain of ancient light. But the CMB is not perfectly uniform, and that imperfection is everything. When the COBE satellite in 1992 first mapped the CMB with sufficient precision to reveal its detailed structure, what it found were tiny variations, temperature fluctuations of about 1 part in 100,000, scattered across the sky in a specific pattern. Those fluctuations were the imprint of density variations in the early universe, regions that were very slightly denser than average, and regions that were very slightly less dense. Those tiny density variations, quantum fluctuations from the universe's earliest moments, stretched to cosmic size by a period of extraordinarily rapid expansion called inflation, became the seeds of all the structure we see today. The slight overdensities collapsed under gravity over billions of years to form galaxies and galaxy clusters and the cosmic web. The voids between them expanded and emptied. Everything you see when you look at the night sky, every star, every galaxy, every structure in the observable universe, traces its origin to those 1 part in 100,000 ripples in the ancient light that Penzias and Wilson first heard as an unexplained hiss in their antenna. Subsequent missions have mapped the CMB in extraordinary detail. The WMAP satellite, operational in the early 2000s, produced a full sky map of those ancient temperature variations with a resolution and precision that transformed cosmology. The Planck satellite, launched in 2009, refined that map further still, measuring the CMB across the full sky with an angular resolution and sensitivity that revealed the geometry, age, and composition of the universe to a precision of better than 1%. From the CMB, cosmologists have determined that the universe is 13.8 billion years old, that it is spatially flat or very close to it, that it is composed of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. The entire standard model of cosmology, our best current understanding of everything the universe is and how it got that way, rests in large part on the information encoded in that faint, ancient hiss detected by two Bell Labs researchers who were trying to get rid of what they thought was noise. There is something I find quietly extraordinary about the cosmic microwave background that I want to leave you with as we move forward. Right now, as you lie in the dark, photons from the edge of the observable universe are passing through you. Ancient light, 13.8 billion years old, that has been travelling since before the Earth existed, since before the Sun was born, since before any star in the Milky Way had ignited. That light is streaming through the walls of your room and through your body at the speed of light, carrying the oldest message in the universe. You're immersed in it always. You swim through it like a fish through water, completely unaware of it, because it is too cold and too faint for any human sense to detect. But it is there. It has always been there. The echo of the beginning, soft and steady and ancient, filling every corner of the sky. The oldest light there is, and it is everywhere. We have spent the last several chapters carefully mapping the boundaries of what we can see. The observable universe, 93 billion light-years across. The cosmic microwave background at its outer shell, marking the moment light first travelled freely. The cosmic event horizon, the line beyond which expansion defeats even light. These are real boundaries, grounded in physics, confirmed by measurement. But tonight I want to take you somewhere that science can point toward but cannot yet fully illuminate. I want to take you past the observable horizon and ask the question that cosmologists ask in quieter moments. The question that sits at the edge of what evidence can tell us and what reason alone must carry forward. What is actually out there, beyond the edge of everything we can see? What lies in the dark beyond our cosmic bubble? Because the observable universe and the actual universe are almost certainly not the same thing, and the difference between them may be the most staggering gap in all of human knowledge. The first and most conservative answer is simply more of the same. More galaxies, more filaments, more voids, more cosmic web, stretching on in every direction beyond our horizon exactly as it does within it. This is actually the prediction of the standard cosmological model, and it is supported by the near-perfect uniformity of the cosmic microwave background. If the CMB looks essentially the same in every direction, and it does to a precision of 1 part in 100,000, then the conditions that produced our observable universe were the same conditions that existed beyond our horizon. The same physics, the same initial density fluctuations, the same processes of galaxy formation. Which means that beyond the edge of what we can see, there are almost certainly more galaxies, more stars, more planets, more of everything. The universe in this picture does not end at our horizon. It simply continues, unseen, into a darkness we can never light. But how much more? Here is where the estimates become truly vertiginous. If the universe is spatially flat, and the best measurements of the CMB geometry suggest it is, or very nearly so, then depending on how flat it is, the total universe could be vastly larger than our observable bubble. Some estimates, based on the measured flatness and the precision limits of our instruments, suggest the total universe must be at least 250 times larger than the observable universe in linear dimensions. That means its volume is at least 250 cubed, roughly 15 million times larger than what we can see. 15 million observable universes, each containing 2 trillion galaxies, each galaxy containing hundreds of billions of stars. The number of stars in the total universe in this picture is so large that it does not fit comfortably even in scientific notation, without feeling like an abstraction that the human mind simply refuses to process. But many cosmologists believe the universe is far larger still. The leading theory of the very early universe, the theory of cosmic inflation, predicts that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion, growing from a region far smaller than a proton to something enormously large in an almost inconceivably short time. Inflation was proposed in 1980 by physicist Alan Guth to solve several puzzling features of the standard Big Bang model, including the extraordinary uniformity of the CMB and the flatness of space. It elegantly resolves those puzzles, but it also carries a startling implication about the size of the universe. If inflation occurred, it almost certainly expanded the universe to a size that dwarfs our observable bubble by a factor that is not millions or billions, but something far beyond any number that words can usefully carry. The total universe, in inflationary cosmology, may be effectively infinite, not very large, not astronomically large, infinite in the mathematical sense with no edge and no boundary in any direction. And if the universe is infinite or even just vastly larger than our observable bubble, then something follows from it that many people find more unsettling than any other idea in cosmology. In an infinite universe, with a finite number of possible quantum states that matter and energy can occupy in any given region of space, every possible configuration of matter must eventually repeat. Every arrangement of particles that can exist will exist, somewhere, infinitely many times, including arrangements that are identical to the observable universe as it is right now, including arrangements that contain a planet exactly like Earth, with a person lying exactly where you are lying, having exactly the same thoughts you're having at this moment. Not similar, identical, down to the position of every atom. This is not mysticism or science fiction. It is a straightforward mathematical consequence of infinity combined with finite quantum states. In an infinite universe, you repeat. You repeat infinitely many times. That idea is either deeply comforting or profoundly destabilizing, and I suspect it depends entirely on who you are and what you need from the night sky. There is another possibility beyond the observable horizon that sits at the frontier of theoretical physics, one that is even more radical. Some versions of inflationary theory predict not just a large or infinite single universe, but an enormous, possibly infinite, collection of separate universes, each with its own physical laws, its own constants, its own history. This is the multiverse, and it comes in several flavors depending on which version of inflationary theory you accept. In the most common version, called eternal inflation, quantum fluctuations in the inflationary field cause it to end in some regions, creating bubble universes like ours, while continuing to inflate in other regions, spawning more bubbles endlessly and without stopping. Each bubble is a universe unto itself, causally disconnected from all the others, expanding into a sea of still inflating space that separates each bubble from its neighbors by distances that grow faster than light can cross them. Our observable universe is one bubble, and the sea beyond it may contain an uncountable number of others, each one a separate cosmos, each one forever beyond our reach. What would those other universes be like? We genuinely do not know. Some physicists believe that the physical constants of nature, the strength of gravity, the mass of the electron, the value of the cosmological constant, are not fixed universal truths, but local parameters that take different values in different bubble universes, determined by the specific way inflation ended in each region. In some bubbles, the laws of physics might be only slightly different from ours. In others, radically different. Different enough that atoms cannot form, or stars cannot ignite, or the universe collapses back on itself before structure can develop. In a tiny fraction of bubbles, the constants might land in the narrow range that permits chemistry, complexity, and life. We live in one of those, not because our universe is specially designed, but because we could not exist to observe it if it were otherwise. This reasoning, called the anthropic principle, is either a profound insight about the relationship between observers and the universes they inhabit, or a frustrating non-answer, depending on your philosophical temperament. Here is what I find most worth sitting with, at the edge of all these ideas. Everything we have discussed tonight, every galaxy, every filament, every structure in the cosmic web, the entire observable universe, with its 2 trillion galaxies and its ancient light, and its expanding horizon, may be an almost infinitesimally small part of something far larger. Our cosmic bubble, for all its staggering scale, may be like a single grain of sand on an infinite beach, and that beach may contain beaches. The universe beyond our horizon is not empty, it is full of something. Whether that something is more of the same, or infinite repetition, or other universes with other laws, we cannot yet say with certainty. What we can say is this: the edge of the observable universe is not the edge of reality, it is only the edge of our sight. And beyond it, the cosmos continues in ways that exceed not just our instruments, but perhaps our imagination itself. I want to take you somewhere unusual tonight, Not outward in space, but forward in time, because the universe is not static. It is not a finished painting hanging on a wall, fixed and permanent. It is a process, a vast, slow, relentless process that has been unfolding for 13.8 billion years and will continue unfolding for spans of time so enormous that the age of the universe as it stands today would be a rounding error by comparison. And when you follow that process forward, when you trace the implications of dark energy and cosmic expansion out into the deep future, what you find is something that most people have never been told, something quietly devastating. The observable universe, as we know it, is not permanent. The galaxies we see tonight will not always be there to see. One by one, over timescales that dwarf all of recorded history, they will vanish, not destroyed, not dimmed, simply carried beyond our horizon, their light stretched to infinity by the accelerating expansion of space, never to return. The universe we see from Earth is not the universe that will exist in the far future, and the universe of the far future will be, in one very real sense, almost empty. Let us start with what is happening right now, in the present cosmic moment. There are currently approximately 2 trillion galaxies within our observable universe. Of those, only a fraction, perhaps a few tens of billions, are gravitationally bound to us in some meaningful sense, either directly or through their membership in the same supercluster. The rest are simply within our line of sight, their ancient light having travelled to us across the expanding cosmos. But as dark energy continues to accelerate the expansion of space, the most distant of those galaxies are already receding faster than light. Their light is still reaching us, as for now, because it left those galaxies long ago when they were closer. But no new light they emit today will ever reach us. They are already, in the most precise sense, sending their last messages, and we are receiving those messages on a delay, like a letter from a friend who has already moved somewhere unreachable by the time the envelope arrives. Project this forward by a few billion years, and the picture begins to change in ways that would be alarming if you could see them unfolding. The galaxies that are currently at the edge of our observable universe will fade and redshift and eventually disappear from our sky entirely, their light stretched beyond any detector's ability to capture. The cosmic microwave background will cool further, dropping from its current 2.7 Kelvin toward temperatures so close to absolute zero that it becomes effectively undetectable. The universe will grow darker and quieter in a very literal sense. But the most significant change will not be in the dimming of distant light. It will be in the loss of entire galaxies from our observable sky. One by one, over timescales of tens of billions of years, the galaxies we see today will cross our event horizon and vanish. Not all at once. Slowly, the way stars fade at dawn, gradually swallowed by a growing cosmic twilight. Look far enough forward, to a time roughly 100 billion years from now, which is roughly 7 times the current age of the universe, and the sky will look very different from any telescope still operating on what remains of Earth or any other world. By that point, the expansion of the universe will have carried all but the gravitationally bound local group of galaxies beyond our event horizon. The great galaxy clusters, the superclusters, the cosmic web with its filaments and voids, all of it will have vanished from view. What remains visible will be only the galaxies gravitationally bound to the Milky Way and Andromeda. The local group. A small, isolated island of matter in an otherwise dark and apparently empty cosmos. A future astronomer born in that era, with no knowledge of the history of astronomy, would look out at their sky and see only a handful of galaxies. They might reasonably conclude that those galaxies were the entirety of the universe. They would have no way of knowing, no observation they could make would reveal, that billions of other galaxies had once populated their sky before the expansion carried them away forever. This is one of the most poignant and genuinely terrifying implications of dark energy that I know. We happen to live at a moment in cosmic history when the universe is still visible in its full complexity. We can see the cosmic web, we can detect the CMB, we can observe the earliest galaxies with instruments like the James Webb Space Telescope, and read the history of the cosmos back to nearly its very beginning. We live in a window of cosmic transparency and richness that will not last forever. We are, in a very real sense, lucky to be here now. A civilization that arose 10 times later than ours, 138 billion years from now instead of 13.8, would be born into a universe that appeared almost empty. The evidence for the Big Bang, for cosmic expansion, for the existence of other galaxies, for everything we know about the large-scale structure of the cosmos would be gone, irretrievably gone, carried beyond the horizon by a process that leaves no forwarding address. Beyond even that timescale, the fate of the universe grows stranger still. In what cosmologists call the era of stellar evolution, the remaining stars in the local group will continue to burn for tens of billions to trillions of years, depending on their mass. The smallest red dwarf stars, the most miserly consumers of hydrogen, will burn for up to 10 trillion years. But eventually all the hydrogen will be exhausted. The stars will go dark. What remains will be white dwarfs cooling slowly toward black dwarfs, neutron stars, black holes, and the faint remnants of planetary systems. No new stars will form, because the gas from which stars are made will have been consumed or dispersed. The galaxies of the local group will gradually dim and fade over trillions of years, like fires slowly running out of fuel, until only cold, dark remnants remain drifting through a dark and silent space. And the black holes? They will outlast everything. A stellar mass black hole will persist for somewhere around 10 to the power of 67 years before it evaporates through the quantum process known as Hawking radiation, a number so large that writing it out in full would fill more pages than there are atoms in the observable universe. Supermassive black holes at the centers of galaxies will last even longer, evaporating over timescales approaching 10 to the power of 100 years or more. But even they are not eternal. Even they will eventually lose their last photon of Hawking radiation and dissolve into a dispersing cloud of particles. After that, the universe will be cold, dark, expanding, and very nearly empty. Physicists call this final state the heat death of the universe. Not death by heat, but death by the complete exhaustion of all differences in energy, a state of maximum entropy where nothing further can happen and nothing further ever will. I want to sit with you in that image for a moment, because I think it deserves to be felt rather than simply noted. The universe will end, in the longest view we can take, in silence and darkness and cold. Every star that ever burned, every world that ever formed, every civilization that ever arose and wondered at the night sky, all of it will eventually be gone, scattered into radiation and cold remnants in an ever-expanding void. That could feel like the saddest possible conclusion to tonight's journey. But I find something else in it too, something almost comforting, because right now, in this cosmically brief and extraordinary moment, the stars are shining, the galaxies are visible, the CMB is still warm enough to detect, the universe is alive with light and structure and complexity, and you are here, in the middle of all of it, aware of it, understanding it, feeling it. That is not nothing. In the vast arithmetic of cosmic time, that is everything. Let us do something that physics does not permit, but imagination does. Let us build a ship, not a ship constrained by the engineering limitations of the 21st century, a perfect ship, a ship that can travel at the speed of light, the absolute maximum that the laws of physics allow for anything with mass, which means we are already bending the rules slightly, but follow me here. A ship with unlimited fuel, unlimited time, unlimited endurance. A ship crewed by you, comfortable and warm, with a window facing forward into the dark, and let us say you have decided to do something no one has ever done. You are going to travel to the edge of the observable universe. You're going to point your ship at the cosmic horizon, fire your engines, and go. I want to walk you through what that journey would actually be like, because it is not what most people imagine, and the reason it is not what most people imagine is one of the deepest and most disorienting truths we have encountered tonight. The first thing you notice, leaving Earth, is that space is extraordinarily empty. The distances between objects are not like the distances in any map you have ever looked at, where the white space between labelled points is just blank paper. In real space, the white space is the point. You leave Earth and accelerate toward the Moon, covering 239,000 miles in just over a second. You pass the Moon and keep going, out through the orbital paths of the planets, past Mars and Jupiter and Saturn, out through the distant reaches of the solar system where the Sun shrinks to a bright point indistinguishable from a very close star. All of this takes minutes to hours at light speed. And then you enter the true interstellar void, the space between stars, and the emptiness becomes something you can almost feel. The nearest star, Proxima Centauri, takes 4.2 years to reach at your speed. 4.2 years of travel, and you have covered a distance that represents roughly 1/25th of a billionth of the diameter of the observable universe. You have not even left the neighborhood. You press on. Crossing the Milky Way takes you 100,000 years at light speed. 100,000 years of travel to cross a single galaxy, and you are still inside our own cosmic island. You exit the far side of the Milky Way and enter intergalactic space, and here the emptiness reaches a new register entirely. The void between galaxies is not like the void between stars. It is more complete, colder, more absolute. The density of matter in intergalactic space is so low, roughly 1 atom per cubic meter, that it makes the vacuum inside our solar system seem crowded by comparison. You travel for millions of years between the scattered galaxies of the local group, then tens of millions more as you cross into the void beyond, heading toward the Virgo cluster, then hundreds of millions as you traverse the cosmic web, passing through filaments where galaxies are dense and bright, then through voids where the darkness is so complete and the nearest galaxy so distant that your window shows nothing but a blackness deeper than anything you have experienced in the inner galaxy. Billions of years pass. You're still traveling at the speed of light. The universe behind you is changing as you go. Stars are being born and dying, galaxies are merging, the cosmic web is slowly evolving. You're not just crossing space, you are crossing time. After a few billion years of travel, you look back and the Milky Way is invisible, lost among the 2 trillion other galaxies too faint and too distant to identify. Ahead of you, the universe looks the same as it did when you left. Galaxies in every direction, arranged in the same web-like patterns, following the same physical laws. You pass through more filaments, more voids, more clusters. The universe does not thin out in the direction you're heading. It does not start to look different, or simpler, or more like an edge. It looks, in every direction, like more universe. The cosmic web repeats its patterns at every scale, in every direction, as far as your instruments can see. After several billion years of travel, something subtle begins to change. The galaxies ahead of you are showing a slight statistical asymmetry. They are on average very slightly younger looking than the galaxies behind you, not dramatically different, but measurably different. This is because you are moving toward the region whose light we see as ancient and distant. The light we receive from these galaxies on Earth was 13 billion years old when it reached us. But you've been travelling toward them for billions of years, closing the distance, and now the light reaching your ship is more recent than what we see from Earth. You are, in a sense, catching up to galaxies that we only ever saw in their youth. Seeing them as they are now, or closer to it, they look older, more evolved, more like the galaxies of the present universe, and less like the young, chaotic structures of the early cosmos. It is a strange and beautiful reversal, travelling toward what we see as the ancient past, and finding the present waiting for you there. Now here is the moment I have been building toward. You have been travelling for most of the age of the universe. You are approaching what we, from Earth, call the edge of the observable universe, the region whose light has been travelling for nearly 13.8 billion years to reach us. And you notice something that is either deeply satisfying or deeply frustrating, depending on what you are hoping to find. There is no edge. There is no wall. There is no place where space ends and something else begins. There is no boundary marker, no change in the texture of reality, no moment where the universe simply stops. What you find at the location we call the edge of our observable universe is more universe, more galaxies, more filaments, more voids, more cosmic web, stretching away in every direction exactly as it did back home. The edge of our observable universe is not a feature of space. It is a feature of our position and our history. Everywhere you go is the center of its own observable universe, its own bubble of visible space. Traveling to our horizon does not take you to the edge of anything. It just gives you a new horizon, centered on wherever you are. And here is the final, most disorienting piece. While you have been traveling for billions of years at the speed of light, the universe has continued to expand. The place you left, Earth, the Milky Way, the local group, is now enormously further from you than when you departed. And the region you are heading toward, the places visible from your new location that were beyond our original horizon, are receding ahead of you as well, carried by the expansion of space. The horizon has moved. The edge of what you can see from your new position has shifted outward. but the expansion has also moved the edge faster than you can chase it. No matter how long you travel, no matter how far you go, the observable horizon retreats ahead of you at the same pace that you approach it, because the universe is expanding in every direction simultaneously. You can travel forever and never reach a final edge, not because the universe is infinite, though it may be, but because every point in the universe is equally central, equally surrounded by its own horizon, and that horizon is always exactly as far away as light can travel in the age of the universe at that moment. The edge of the universe is not a place you can reach. It is a circle that moves with you wherever you go. And that, perhaps more than anything else we have discussed tonight, is the true measure of how strange and how vast the cosmos actually is. On the 25th of December, 2021, a rocket lifted off from the Guiana Space Center on the northeastern coast of South America, carrying the most complex and expensive scientific instrument humanity had ever built. The James Webb Space Telescope had taken more than 25 years and approximately $10 billion to design, build, and launch. It had been described, not entirely hyperbolically, as a machine for seeing the beginning of time. Its primary mirror, a honeycomb of 18 gold-coated hexagonal segments unfolding in space like a flower, stretched 6.5 meters across, more than 2.5 times the diameter of the Hubble Space Telescope's mirror. Its sun shield, a 5-layered membrane the size of a tennis court made of a material thinner than a human hair, was designed to keep its instruments at temperatures approaching negative 233 degrees Celsius, just 40 degrees above absolute zero. It needed to be that cold to see what it was designed to see. The faintest, most ancient light in the observable universe, stretched by cosmic expansion into the infrared, invisible to human eyes and to most instruments that came before it. When it reached its destination, a gravitationally stable point in space about 1.5 million kilometers from Earth, and its systems were tested and calibrated over the following months, what it sent back changed our picture of the early universe in ways that scientists are still working to fully understand. The first full-color images from JWST were released in July of 2022, and the reaction from the scientific community and the public alike was something between euphoria and disbelief. One of those first images, a deep field photograph showing a patch of sky roughly the size of a grain of sand held at arm's length, contained thousands of galaxies. Some of them were among the most distant objects ever imaged. Their light had been travelling for more than 13 billion years before entering the telescope's mirror. We were seeing those galaxies as they existed when the universe was less than 1 billion years old, less than 7% of its current age. Infant galaxies, caught in the act of forming, their stars young and hot and blue, their shapes chaotic and irregular, nothing like the elegant spirals and ellipticals we see in the more evolved universe around us today. It was, in the most literal possible sense, a photograph of the past. A window opened onto an era of cosmic history that no human instrument had ever seen with such clarity or such depth. But JWST did not just show us what the early universe looked like. It showed us things that were not supposed to be there. Galaxies that were too large, too massive, too well formed for how early they appeared in cosmic history. Standard models of galaxy formation, our best theoretical understanding of how dark matter halos collapse under gravity, accumulate gas, and ignite into star-forming systems, predicted that the very early universe should contain small, irregular, chaotic proto-galaxies just beginning the long process of growth. What JWST found instead, at redshifts corresponding to times less than 700 million years after the Big Bang, were galaxies with stellar masses comparable to the Milky Way today. Mature-looking systems, rotating with apparent order, containing stars of different ages suggesting multiple generations of star formation, had already occurred. They were, in the blunt assessment of several leading cosmologists, galaxies that should not exist at that point in cosmic time. Not impossible, necessarily, but deeply challenging to the models we had spent decades refining. The reaction from the cosmological community was not panic, but it was genuine excitement of the kind that scientists feel when the data pushes back against theory. Some researchers suggested that the early universe may have formed stars far more efficiently than models predicted, that gas collapsed into stars faster and in greater quantities than the simulations had suggested. others proposed that some of the apparent early massive galaxies might be the result of gravitational lensing, the bending of light by massive foreground objects that can make background galaxies appear brighter and therefore closer than they are. Still others suggested that our understanding of dark matter's role in early galaxy formation needed revision. No single explanation has yet won consensus. The data from JWST is still being processed, analysed and debated by researchers around the world. What is clear is that the early universe was more active, more structured, and more complex at earlier times than our previous best models allowed. The universe, it seems, got to work faster than we thought. JWST has also pushed the observational frontier in another direction, the search for the very first stars and the very first black holes. The first generation of stars are called Population 3 stars, a designation that reflects the fact that they are the oldest stellar generation, containing no elements heavier than hydrogen and helium, because no previous stars had yet forged heavier elements in their cores, have never been directly observed. They are too ancient, too distant, and too faint for any previous instrument. JWST has not yet definitively detected Population 3 stars, but it has observed signatures in some distant galaxy spectra that are consistent with what those ancient stars would produce. Intense ultraviolet radiation, unusual chemical abundances, the fingerprints of a stellar generation made entirely of the universe's original hydrogen and helium. If those detections are confirmed, it will be one of the most significant discoveries in the history of astronomy, the first direct evidence of the very first stars that ever shone in the universe. There is something I want to pause on here, because I think it gets lost in the technical detail. The James Webb Space Telescope is, among other things, a machine for confronting our own ignorance. Every time it reveals something unexpected, a galaxy too massive too soon, a structure too ordered too early, a signature too complex for such a young universe, it is not disproving science. It is doing what science is designed to do. It is finding the edges of our current understanding and showing us exactly where those edges are. Every surprising result from JWST is not a failure of cosmology. It is an invitation to look again more carefully, to revise our models, to ask better questions. The universe is not obligated to fit our theories. Our theories are obligated to fit the universe. And JWST is holding us to that standard with extraordinary, unforgiving precision. Perhaps the most remarkable thing about JWST, and the most relevant to everything we have been discussing tonight, is what it represents in the long human project of pushing back the observable horizon. Galileo pointed a small tube of glass and lenses at the sky in 1609 and saw moons orbiting Jupiter, craters on the moon, and more stars than the naked eye could count. That instrument extended human vision into a realm that had been invisible to every human who had ever lived before him. Each generation of telescopes since then has pushed that horizon further. Larger mirrors, higher orbits, new wavelengths, and now JWST, floating cold and golden in space 1.5 million kilometers from home, is pushing our observational frontier closer to the Big Bang than we have ever been. It is seeing light that has been travelling since the universe was a few 100 million years old. We are, with this machine, nearly reaching the limits of what light can show us about cosmic history, nearly reaching the wall of the CMB itself. And what we are finding at that wall is that the universe was stranger, richer, and more surprising than we imagined. It almost always is. Here is a number I want you to hold in your mind for a moment. 5. Just 5. As in 5%. That is the fraction of the total content of the universe that is made of ordinary matter. The stuff of stars, planets, gas clouds, dust, comets, asteroids, oceans, mountains, trees, and every atom in your body. Everything you have ever seen, touched, tasted, smelled, or measured. Every instrument humanity has ever built. Every telescope, every probe, every particle accelerator, all the galaxies in the observable universe, all 2 trillion of them, with all their hundreds of billions of stars each. All of that, every shining, glowing, radiating thing in the cosmos, adds up to approximately 5% of what the universe actually contains. The other 95% is something else entirely, something we cannot see, something we cannot touch, something we have never directly detected and do not yet fully understand. And when I tell you that this is one of the most solidly established facts in modern cosmology, confirmed by multiple independent lines of evidence, I want you to feel the full weight of what that means. Almost everything that exists is invisible to us, permanently, completely, by the nature of what it is. The first major component of that invisible 95% is dark matter, which makes up approximately 27% of the universe's total energy content. Dark matter is not dark in the sense of being black or absorbing light. It is dark in the sense of being completely transparent to light. It neither emits nor absorbs nor reflects electromagnetic radiation of any kind. It passes through ordinary matter almost without interaction. Right now, as you lie in the dark, an estimated hundreds of thousands of dark matter particles are passing through your body every second, through the floor beneath you, through the earth itself, passing through as if ordinary matter did not exist, leaving no trace, exerting no measurable force beyond gravity. We know dark matter is there only because of what it does gravitationally. The way it bends light from distant galaxies, the way it holds galaxy clusters together against forces that would otherwise fling them apart, the way galaxies rotate at speeds that make no sense unless there is far more mass present than the visible stars and gas can account for. This story of dark matter's discovery begins in the 1930s with a Swiss astronomer named Fritz Zwicky, who was studying the Coma Cluster, a dense collection of galaxies about 320 million light-years from Earth. Zwicky measured the velocities of the galaxies within the cluster and noticed something deeply wrong. The galaxies were moving far too fast. At the velocities he measured, the gravitational pull of all the visible matter in the cluster, all the stars, all the gas, everything he could see, should not have been enough to hold the cluster together. The galaxies should have flown apart long ago. The cluster should not exist, but it did exist, and it was stable. Zwicky concluded that there must be an enormous amount of additional mass in the cluster that he could not see. He called it Dunkelmaterie, dark matter. The astronomical community largely ignored him for decades. Then, in the 1970s, astronomer Vera Rubin measured the rotation curves of individual galaxies and found the same problem on a smaller scale. Stars at the outer edges of galaxies were orbiting far too fast for the visible mass of those galaxies to account for. Dark matter, distributed in vast halos around and beyond the visible extent of each galaxy, was the only explanation that fit. The field has never been the same since. Despite decades of searching, we have never directly detected a dark matter particle, not once. Experiments buried deep underground in mines, shielded from cosmic rays, filled with ultra-sensitive detectors looking for the faintest whisper of a dark matter interaction with ordinary matter, have found nothing definitive. Particle accelerators that smash protons together at nearly the speed of light, creating showers of exotic particles, have produced no confirmed dark matter candidates. Astronomical searches for gamma-ray signatures that dark matter self-annihilation should produce have found hints but no confirmed signals. We know dark matter exists. The gravitational evidence is overwhelming and multiply confirmed, but we do not know what it is made of, what its fundamental properties are, or why it interacts with gravity but apparently nothing else. It is one of the most tantalizing open questions in all of physics. A thing we can map but cannot touch, cannot identify, cannot explain with any particle in the standard model of particle physics. And then there is dark energy, the 68%, the dominant ingredient. We discussed dark energy earlier in our journey tonight, but I want to return to it here in the context of the full accounting of what we cannot see, because its mystery is of a different and perhaps deeper character than dark matter's. Dark matter, whatever it is, behaves like matter. It clusters gravitationally, it forms halos, it participates in the structure of the cosmic web. We can map its distribution. We can model how it behaves even without knowing what it is. Dark energy is stranger. It does not cluster. It does not clump. It does not form structures. It is perfectly, smoothly distributed throughout all of space at a constant density, filling every cubic centimetre of the universe equally, regardless of what else is in that cubic centimetre. It acts not as a gravitational attractor, but as a gravitational repulsor at the larger scales, pushing the universe apart rather than pulling it together, and its density does not change as the universe expands, which means the total amount of dark energy in the universe grows as space itself grows. It is energy that comes from nowhere, or rather from the very nature of space itself, and it is the dominant force shaping the fate of everything. Here is the thing most people do not realize when they hear these numbers for the first time. The gap between what we can see and what exists is not a small oversight. It is not a minor correction to an otherwise complete picture. It is the picture. When physicists say we understand the universe, what they actually mean is that we have an excellent mathematical description of 5% of its contents and a functional but deeply incomplete characterization of the other 95. The standard model of particle physics, the most precisely tested theory in the history of science confirmed by experiment after experiment to extraordinary precision, describes only the 5%. It has nothing to say about dark matter. It has nothing to say about dark energy. The most successful theory of matter humanity has ever produced is, in the most literal sense, a theory of the minority ingredient. We have built our entire scientific understanding of the physical world on a foundation that accounts for less than 1/20th of what is actually there. What I want you to take from this chapter is not despair. It is not the feeling that science has failed or that knowledge is futile. Quite the opposite. The fact that we know we are missing 95% is itself a profound scientific achievement. A century ago, we did not know dark matter existed. We did not know dark energy existed. We thought the visible universe was the whole universe. The discovery of our own ignorance, the mapping of the boundaries of what we know, is one of the great accomplishments of modern cosmology. You cannot solve a problem you do not know you have, and now we know, with extraordinary precision, exactly where the gaps are. We know that 5% of the universe is ordinary matter. We know that 27% is dark matter. We know that 68% is dark energy. We have weighed the unknown and found it vastly heavier than the known. And that is not the end of the story. It is the most exciting possible beginning. Because somewhere in that 95%, in the nature of what we cannot see and cannot yet explain, may lie the deepest truths about what the universe actually is. I want to stop here, just before the end, and ask you something. Not a rhetorical question this time, a real one, the kind that deserves a moment of genuine stillness before you let it pass. How did we figure all of this out? How did a species that evolved to find food, avoid predators, and navigate the social complexities of small tribal groups on a single small planet, how did that species with those brains, with those eyes, with those hands, manage to map a universe 93 billion light-years across? How did we determine the age of the cosmos to within a fraction of a percent? How did we detect the faint afterglow of the Big Bang, distinguish the signatures of dark matter from ordinary matter, measure the acceleration of cosmic expansion, and peer back to within a few 100 million years of the universe's origin? We did it without leaving our solar system. We did it for the most part without leaving the surface of our planet. We did it using light, mathematics, and the extraordinary, improbable fact that the human mind is capable of understanding things that have nothing whatsoever to do with its own survival. That is not a small miracle. That is perhaps the most astonishing thing I know. The atoms in your body are old, genuinely, cosmically old. The hydrogen atoms in the water molecules in your cells were forged in the first few minutes after the Big Bang, 13.8 billion years ago, in a burst of primordial nucleosynthesis when the universe was hot enough to fuse protons and neutrons together. Those hydrogen atoms have been part of the universe for nearly its entire existence. They have drifted through interstellar space, been swept into molecular clouds, been incorporated into stars, been expelled in stellar winds and supernova explosions, been scattered across light years of space, and eventually, after billions of years of cosmic wandering, found their way into the chemistry of a planet orbiting a young star in the outer arm of a spiral galaxy. Into the oceans of that planet, into the cells of life, into you. The heavier elements in your body, the carbon in your DNA, the oxygen in your blood, the calcium in your bones, the iron in your hemoglobin, were made in the cores of stars that lived and died before the sun was born, forged in the nuclear furnaces of stellar interiors and scattered by supernova explosions across the galaxy. You are, in the most chemically precise and literal sense possible, made of star stuff. You are the universe, shaped by 4 billion years of biological evolution into a form capable of looking back at itself and asking where it came from. This is what the physicist Carl Sagan meant when he said that we are a way for the cosmos to know itself, and it is what the philosopher and cosmologist Brian Swimme meant when he described the human being as the universe reflecting on its own nature. These are not poetic exaggerations. They are descriptions of something genuinely true and genuinely extraordinary. For 13.8 billion years, the universe expanded and cooled and structured itself into stars and galaxies and planets, and chemistry and life and mind. And then, in the last cosmically negligible instant, the last few 100,000 years out of 13.8 billion, it produced creatures capable of measuring its own age, capable of detecting the echo of its own birth, capable of calculating the distance to its own horizon. The universe has, through us, become aware of itself, and I find that fact more moving than almost anything else that has ever been said about the human condition. Think about what it took to get here, not just the biological evolution, though that alone is staggering. 4 billion years of mutation and selection and extinction and adaptation, a process of almost inconceivable complexity that produced, among other things, the nervous system you're using right now to process these words, but also the cultural evolution, the first humans who looked up at the night sky and wondered, the ancient Babylonians who track the movements of planets with enough precision to predict eclipses, the Greek philosophers who proposed that the Earth was round and estimated its circumference with surprising accuracy using shadows and geometry, Copernicus, who displaced the Earth from the centre of the universe, Galileo, who turned a glass lens to the sky and saw things no human eye had ever seen, Newton, who found the mathematics of gravity hiding in the motion of planets and falling apples, Einstein, who showed that space and time were not fixed stages but dynamic participants in the drama of the cosmos, Hubble, who discovered that the universe was larger and older and more magnificent than anyone had imagined, and the thousands of scientists who followed, the Vera Rubins and Alan Guths and Saul Perelmutter's, and the teams behind Planck and WMAP and JWST, each one standing on the shoulders of everyone who came before, each one pushing the horizon a little further back, each one asking one more question of the dark. All of that, every step of that long journey of understanding, happened on one small rocky world orbiting one unremarkable star, in the outer arm of one galaxy among 2 trillion, in a corner of the observable universe so ordinary that there is nothing to distinguish it from millions of similar locations. We are not at the centre of the universe. We are not in a special place. We are not, as far as we can tell, unique in the sense of being the only planet with life, or the only civilization with curiosity. We are simply here, in this particular moment of cosmic time, with these particular brains looking out at this particular patch of the observable universe. And what we have managed to understand from this position, this tiny, peripheral, unexceptional position, is breathtaking. We have measured the universe. We have dated it. We have mapped its structure from the smallest quantum scales to the largest cosmic filaments. We have traced its history from the first fractions of a second after its birth to the far distant future when the last black holes will evaporate into cold radiation. All of that. From here. From this. I think about the people throughout history who looked up at the same sky you're under tonight and felt the same pull of wonder you feel. The shepherd, lying in a field 3,000 years ago, watching the Milky Way arc overhead, with no words for what it was but with the same sense of smallness and awe that you carry right now. The sailor navigating by starlight across a dark ocean, trusting the sky as a map because the sky was the only map there was. The child who asked why the stars do not fall and never quite got a satisfying answer and grew up still wondering. Every human who ever lived has looked at the same night sky, the same stars roughly in the same patterns, broadcasting the same ancient light, and all of them, across all those centuries and cultures and languages, felt some version of what you are feeling right now. That pull, that question, that sense of being very small in something very large, and finding that strangely comforting rather than frightening. Because here is what I think is the deepest truth in everything we have covered tonight. The universe is vast beyond comprehension. 93 billion light-years of observable space, filled with 2 trillion galaxies, woven into a cosmic web of filaments and voids, expanding faster every second under the influence of a dark energy we cannot explain, surrounded by an even larger unknown that may be infinite and certainly exceeds our sight. Most of it is invisible to us. Most of it is unreachable. Most of it will one day vanish beyond our horizon. leaving us in an apparent cosmic solitude that future civilizations may not even realize was not always there. The universe does not need us. It was here for 13.7 billion years before we arrived, and it will be here for an almost unimaginable span after we are gone. It owes us nothing. It was built by no one for our benefit. And yet here we are inside it, made of it, capable of understanding it, capable of being moved by it, capable of lying in the dark on a quiet night and feeling something that might be the closest thing the universe has to wonder at itself. We are not observers of the universe. We are the universe, briefly, beautifully, improbably awake. We have come a long way tonight, you and I. We started in the dark with that feeling you know, the one that comes when you look up and the sky opens and something in you goes very quiet. We took that feeling seriously. We followed it outward, past the moon and the planets and the edge of the solar system, out through the galaxy, across the intergalactic void, through the cosmic web of filaments and superclusters, all the way to the outer shell of the observable universe, where the oldest light in existence still washes over us like a tide that has been travelling since before the Earth was born. We looked at the expanding universe and understood why distance in the cosmos is not a fixed number, but a moving, growing, accelerating thing. We stood at the cosmic event horizon and felt the vertigo of knowing that most of what we can see is already beyond our permanent reach. We imagined travelling to the edge and found that the edge moves with us wherever we go, and we looked at the 5% of the universe that we can see and sat in honest silence before the 95% that we cannot. That was not a small journey. That was about as far as the human mind can go. I want to spend these last few minutes not adding more information, but helping you settle into what you now carry. Because I think there is something that shifts in a person when they truly absorb the scale of the universe. Not just intellectually, not just as a collection of impressive numbers, but in the quiet, bodily way that real understanding moves through you. The universe is 93 billion light-years across, observable. It is almost certainly far larger than that, perhaps infinitely so. It is 13.8 billion years old and expanding faster every second. It contains 2 trillion galaxies within our sight alone, each one a home to hundreds of billions of stars, each star a sun, many of those suns orbited by worlds. Almost all of it is invisible to us, dark matter and dark energy filling the spaces between everything we can see, shaping the fate of the cosmos from behind a veil we have never pierced. And all of this, all of it, is, as best we can tell, just one bubble in a perhaps infinite sea of other universes, each one born from the quantum fluctuations of an inflationary field that may never stop producing new cosmoses in the space between the ones that already exist. You're a small creature in an incomprehensibly large place, and you understand that now, a little more than you did at the beginning of tonight. That matters. That is not nothing. Here is what I find most worth holding on to in the quiet before sleep. You're at the centre of your own observable universe. Not metaphorically, literally. The observable universe is defined by what any given observer can see, and you are the observer. Every point in space is the centre of its own cosmic bubble, which means that wherever you are, in whatever room, in whatever city, on whatever continent, the universe extends equally in every direction from where you lie. 46 billion light-years of observable space radiates outward from you in every direction, like the spokes of an infinite wheel. The most distant light in the universe is arriving at your location right now, from every direction simultaneously, ancient photons from the edge of the observable cosmos passing through the walls and through your body, and through the space between your atoms at the speed of light. You are, at this moment, being touched by the oldest light there is. The universe is making contact with you continuously from its furthest reaches, with messengers that have been travelling since before the Earth existed. You're not separate from the cosmos. You're where the cosmos arrives. I think about what it means to live a human life in the context of everything we have discussed tonight. The worries that feel enormous at 2 a.m, the conversations that went wrong, the decisions that feel impossible, the weight of all the things undone. They do not disappear when you hold them next to the scale of the universe. I will not pretend that they do, but something changes in their texture. Something about knowing that you exist at the centre of a 93 billion light-year observable sphere, on a pale blue dot orbiting a middle-aged star, in a galaxy that is one of 2 trillion, in a universe that has been expanding for 13.8 billion years, and will continue expanding for timescales that make that number look like a heartbeat. Something about knowing all of that makes the present moment feel simultaneously very small and very precious. You are here, you are aware, you are in the most literal sense the universe looking at itself, and you are doing it right now, in this particular moment, in this particular life, on this particular night. That specificity is not a limitation, it is a gift. There will come a night, some future night, perhaps soon, perhaps years from now, when you step outside and look up and the sky is clear and dark and full of stars. I want you to remember tonight when that happens. I want you to remember that the stars you see are not just pretty lights scattered across a flat ceiling of sky. They are suns, hundreds, thousands of them, each one burning at temperatures of millions of degrees, each one light years away, each one a sun that burned and died and scattered its atoms long before you were born. The light entering your eyes when you look at a star has been travelling for years, or decades, or centuries, or millennia before it reached the specific location in space and time where your eyes happen to be. You're seeing the past. You're reading a message sent across the light years by a fire that may no longer even be burning. And behind those stars, invisible to the naked eye but real beyond any doubt, are 2 trillion galaxies stretching away to a horizon 46 billion light years out, filled with structures and mysteries and ancient light and dark matter, and the quiet, relentless expansion of space carrying everything in the universe gently, permanently, inevitably apart. All of that is up there, every night, whether you look or not, whether anyone looks or not. The universe does not require an audience. It does not need to be observed to be real, but there is something that happens when it is observed, when a conscious mind turns upward and tries to comprehend it, that feels to me like the most important thing a mind can do. Not the most productive, not the most practical, the most important. Because in those moments of genuine cosmic wonder, something in us remembers what we are and where we come from, and how brief and strange and luminous this existence is. We remember that we are made of the ashes of dead stars, that we are built from matter forged in the hearts of suns that burned out before our planet existed, that we are in every atom of our bodies continuous with the universe that made us, and that the night sky is not something separate from us that we look up at. It is something we are part of, something we are made of, something we are. Thank you for joining me tonight. Truly. There is something I find genuinely moving about the fact that you chose to spend these hours here, letting these ideas wash over you in the dark, following the light to the edge of everything and back. If you found something in tonight that stays with you, some shift in how the sky looks, some new feeling when you think about distance or time or light, then this journey was worth every step. If you loved exploring the depths of space tonight, please take a moment to like this or subscribe to Calm Space. It is a small thing, but it helps us reach more curious minds who are lying awake somewhere in the dark, looking for exactly this. The next time you look up at the night sky, remember that the light reaching your eyes has crossed distances that would take billions of years to travel. Remember that you are at the center of your own observable universe. Remember that the cosmos is almost entirely unknown, and that the unknown is not something to fear but something to wonder at, quietly in the dark just before sleep. The universe is vast and strange and ancient and expanding and mostly invisible and more beautiful than anything we have words for. And you are part of it. You have always been part of it. Sleep well tonight.